In this video, I'm going to take a look at the Physical Sciences Paper 1, November 2024. Let's start with multiple choice. Question 1.1. Several forces are acting on a moving object. Which one of the following statements is correct when these forces are in equilibrium? So I will write here question 1. And let's use a blue pen here. 1.1. If the forces are in equilibrium, will the object be moving at, or will the velocity be increasing? Will it be moving at a constant velocity? Will the kinetic energy be decreasing, or will the object have a non-zero acceleration? So when something is in equilibrium, it means that F net is equal to 0. So if F net is equal to 0, it means that the acceleration is equal to 0, which means that it is moving at a constant velocity. So the answer to this question is going to be B. Question 1.2. A stone is thrown vertically downward from the top of a building. Takes t seconds to strike the ground. Consider the acceleration time graph below for the motion of the stone. The effects of air friction are ignored. So what does the shaded area between 0 and t seconds shown in the graph represent? Does it represent the final velocity, the change in position, the constant velocity, or the change in velocity? So if we're working out area here, remember that the area, and that's a rectangle, is going to be length times breadth. So doesn't matter which you use as length or breadth. Let's just use acceleration multiplied by time. So we want to figure out what is acceleration divided by time. So we look at the formula for acceleration. Acceleration is equal to the change in velocity divided by time. So if I rearrange this, a times time is equal to the change in velocity. So the answer here, I'm going to pick D. Moving on to question 1.3. A ball moving horizontally has a constant momentum P and kinetic energy K. The ball collides with a wall and moves back horizontally. Immediately after the collision, the ball has momentum half P. The mass of the ball remains constant. Which one of the following is the kinetic energy of the ball immediately after the collision? So I'm going to write here, before the collision, the momentum is equal to m times v, and kinetic energy K is equal to half mv squared. But after the collision, now remember, to get a momentum of half, and if mass is the same, it must mean that the velocity has been halved. So we're going to have half p is going to equal m times half v. Because again, the only way to get half the momentum, if the mass is the same, is to half the velocity. So now let's substitute that in the kinetic energy formula. So K is equal to half m, and now the velocity is half v squared. So that's going to equal half m times a quarter v squared. I can then take the quarter out to the front. A quarter times half mv squared, which is equal to a quarter k. So the answer here is going to be A. Moving on now to question 1.4. A force F acts on a box as the box moves from rest down a rough incline at constant acceleration. The force is parallel to the incline as shown in the diagram below. Choose the option that correctly completes the following statement. The work done by the gravitational force is something. So is it equal to the sum of? Is it less than the sum of? greater than the sum of or equal to the difference between the work done by the frictional force and the work done by F. Now I'm going to draw a free body diagram just to make it a bit easier to understand what's going on. So the forces that we are going to be interested in here are definitely going to be, well, the force applied. It's moving down, so friction is going to be up the slope. And there's going to be W parallel going down the slope. And we have the object moving downward, so like so. Now I can use, well, what is F net going to be? Well, F net is going to be, if I'm choosing down as positive, W parallel minus the force applied minus friction. So we can then use the work formula. We can say that W net is equal to delta EK. So W net can be rewritten as F net times delta X, and that's equal to, now since the object started at rest, its initial kinetic energy is 0, so the change in kinetic energy is only going to be half mv final squared. Now we know what F net is. F net is W parallel minus the force applied minus friction, and then multiplied by delta X, and that's going to be half mvf squared. Now from here I can get the work done. So if I multiply each thing that's inside the bracket by delta X, I will get the work. So the work done by gravity, so the work done by W parallel, minus the work done by the force applied, minus the work done by friction, is going to equal half mvf squared. Now let's rewrite this. I'm going to say W, well, the work done by gravity in this case, minus, open bracket, the work done by the force applied, plus the work done by friction, is going to equal half mvf squared. Now you could get to this point much quicker, but I've just shown you steps. Now because it is moving down the slope, its final velocity is going to end up being positive. Well, it's going to be positive anyway, and that means that this side of our equation is going to be positive, because you're squaring it and you're multiplying by half the mass. So that's going to be positive. Now, on the left-hand side, for the left-hand side to be positive, and it has to be positive, the work done by gravity, must be greater than the sum of the work done by the force applied and the work done by friction. Because if it wasn't, then we would have a negative on the left-hand side, which is obviously not correct. So the answer here is going to be C. Question 1.5. A ball falling vertically downward from point A strikes the ground with velocity v and bounces, reaching a maximum height at point B as shown in the diagram below. Which of the following combinations is correct regarding the impulse and regarding the velocity at which the ball leaves the ground? So impulse is F net times delta t, and it's equal to the change in momentum. So the final momentum minus the initial momentum. Now if we think about the momentum of this object, as it's traveling down, its momentum is downward, right? And then once it hits the ground, its velocity is negative, and so its momentum is going to be negative. So its momentum here is going to be upward, right? So that means the change in its momentum, it changed from negative, from positive to negative, or from down to up. So the change here is upward. So that means the impulse must be upward as well. So we have option A and option C. Then the magnitude of the velocity with which the ball leaves the ground. So they show us here and they tell us that the ball stops at point B, and we can see that point B is lower than point A. So that means that its velocity, okay, so let me just write it out here. So the lower height at point B means that it must have had less energy to get there. So it had a lower EK on that first bounce. And because it had a lower EK, it must have had a lower velocity. So the answer we're going to choose is going to be option C. Moving on to question 1.6. The absorption spectrum of an element surrounding a moving star is observed and it is found to be redshifted. So here this is mostly a theory question. If something is redshifted, it's moving away from us. So we have option A and option C. Then the frequency of the observed light. So here we have to, well, just remember that red is on the high wavelength end of the spectrum. And because wavelength and frequency are inversely proportional, it's going to have a low frequency. So the answer here is going to be away from Earth and decreased frequency. The answer is going to be A. Question 1.7. Two small identical spheres, each with a mass m and charge q, are placed in a vertical cylinder. The spheres remain stationary when their centers are r meters apart as shown in the diagram. Which one of the following expressions can be used to correctly calculate the distance r? Now, I'm going to draw a free body diagram for this sphere right here. So the forces that are acting on that sphere are going to be the force of gravity, and it is going to be the electrostatic force. Now, the force of gravity is going to equal the electrostatic force because it's stationary, right? So F net is equal to 0, which means that Fe is equal to Fg. Now Fe is equal to K Q1 Q2 divided by R squared, and that's equal to mg. Now because the charges are the same, we can rewrite this as kq squared divided by r squared, and that's equal to mg. Now we want to solve for r, so let's switch the r squared over. So kq squared divided by mg is equal to r squared. Now we can square root, so the square root of kq squared divided by mg is equal to r. So the answer we're going to choose is answer option A. Question 1.8. The kilowatt hour, so kWh, is a unit of power, electric current, energy, or potential difference. This is a theory question. 1.8. It is a measure, it is a unit of electrical energy, option C. Question 1.9. The diagram below shows a simplified electric motor. The rotation of the coil is observed from the battery. Which one of the following statements is correct while the motor is in operation? Now, we can clearly see that this is a split ring. So option A and B are out. Now we need to use our left hand because this is a motor. So if we are using our left hand, our index finger is pointing to the right, remember, pointing from north to south. The current is actually going to point away from us, because remember, current flows from the positive terminal to the negative terminal, and that means that the force is pointing down. So this side of the coil is going to go down, and this side of the coil is therefore going to go up, meaning it's spinning this way. So question 1.9, the commutator rotates anti-clockwise. The answer is D. Question 1.10, which of the following statements is or are true for the photoelectric effect? The photoelectric effect demonstrates that light has a wave nature, particle nature, or that light is quantized. So the answer here is going to be the second one and the third one. So the answer here is D. Question number 2. In an experiment, a crate of mass 8.5 kilograms lying stationary on a rough horizontal table is connected to a mass hanger by means of a light inextensible string passing over a frictionless pulley as shown in the diagram. Mass pieces are added to the mass hanger and the acceleration of the crate is measured. The experiment is repeated several times by adding different masses to increase the hanging mass each time. Ignore the effects of air friction. The results obtained were used to draw the sketch graph below. Question 2.2. Draw a labeled free body diagram showing all the horizontal forces acting on the crate just before it starts moving. So it's not moving, which means that the forces, should be in equilibrium, and they are in equilibrium. And the question is only asking for the horizontal forces. So the forces we will draw are going to be the tension and friction. Question 2.3.1. Calculate the coefficient of static friction. Now again, remember, this is while it is stationary. So we can say that F net is going to equal MA. Since it is stationary, we can say that F net is going to equal 0. Now, assuming that we are talking about the 8.5 kilogram block, the forces acting on it, I'm going to choose right as positive. So T minus F is equal to 0. That means T is equal to F. Now, if we look at the hanging mass, we can read the graph here, and the hanging mass is stationary when the mass is 4.2 kilograms. So for the 4.2 kilogram block, I'm going to say again that F net is equal to 0. Now, when it's hanging, when that mass piece is hanging, there's only two forces acting on it, one being tension and one gravity. So if I've chosen right as positive here, then I must choose down as positive here, because it kind of connects like that, you see. So I'm going to have gravity minus tension is equal to 0. That means the force of gravity is equal to tension. So if I want to work out, and the question is asking what is the coefficient of static friction, if I can work out what the tension is, then I can work out what the coefficient of friction is. So the tension, I can start by calculating it from here. So mg, so 4.2 multiplied by 9,8 is my tension. And that means my tension is equal to 41.16 newtons. Now, the same tension is on the 8.5 kilogram block. So 41.16 is equal to, friction is mu s times Fn. Now 41.16 is equal to mu s, and Fn, since the block is on the table, Fn is going to equal gravity, the force of gravity. So it's going to be 8.5 multiplied by 9.8. So we can solve for mu s, and that's going to give us 0.49. There's no units there. Let me just separate this so it looks a bit more neater. So we start here and we end here. Now question 2.3.2, calculate the magnitude of the acceleration represented y on the graph if the coefficient of kinetic friction between the crate and the table is 0,40. Now what we'll do here is we will repeat the process. Now for my 8.5 kilogram block, so 8.5 kilogram, I'm going to have F net equal ma. But in this case, it's not going to equal 0 because it's clearly accelerating. That's according to the graph. So we're going to have T minus friction is equal to ma. So 8.5 multiplied by the acceleration. Now, the friction value is going to be different because they've given us a new kinetic friction or coefficient. So T minus, and again, friction is going to be mu s, or mu k rather, mu k times Fn. So that's going to be 0.4 multiplied. Fn is going to be the force of gravity. So that's going to be 8,5 times 9,8. And that's going to equal 8,5a. And that's going to be one equation. Now, let's take a look at the hanging mass. So at y, when the acceleration is y, the hanging mass has a mass of 7.4 kilograms. So 7.4 kilogram mass, we are going to have Fg minus tension equal ma. So Fg is going to be 7.4 multiplied by 9,8 minus the tension is going to equal 7.4 a. Now we can make them the subject of the formula, or make t the subject of the formula for both of them, and then we can equate. Remember, this is now a simultaneous equation. So we will have 8.5a plus, now I'm taking this whole thing over, 0.4 into 8.5 times 9,8. That's going to be tension, and that's going to equal, on this side I'm going to have minus 7.4a, and then I'm going to have plus 7.4 into 9,8, and that's going to be t as well on this side. And now I can solve for a. A is going to equal 2,47 meters per second squared, and that's going to be to the right, or it's going to be down depending on which mass block or mass piece you are referring to. You could say clockwise also, I mean, because it's moving right and down, so it's moving clockwise. But the question is asking for the magnitude of the acceleration, so it's not really necessary. Question 2.4, a 5 kilogram block is now placed inside the crate and the experiment is repeated. How will this affect the maximum static friction force experienced by the crate? So remember, Fs max, so this is question 2.4, Fs max is equal to mu s multiplied by Fn. Now we know that Fn is m times g, and that's going to be mu s, and that's going to be Fs max. Now the coefficient is the same, gravity is the same, so that means that m, well, Fs max is directly proportional to m. So if m increases, like they are explaining here, Fs max is also going to increase. Question 3 says a ball A is thrown vertically upward at 12 meters per second from the top of a building. 2 seconds after ball A was thrown upward, ball B is thrown vertically downward at 5.4 meters per second from the top of the same building. Both balls A and B strike the ground at the same time. So at the same time. I'm going to highlight the bits that I feel are important. thrown vertically upward 12 meters per second. 2 seconds after ball A was thrown, ball B is thrown downward at 5.4 meters per second, and they strike the ground at t seconds. So we've been given this graph, and the question says, using equations of motion only, calculate the value of each of the following as shown in the graphs. So they want to know 3.1.1, calculate the value of t. So what is the time at which both these balls hit the ground? So I'm going to write out here 3.1.1. I'm going to first write out the quantities that I know. So for VI, for object A, I know that the initial velocity is 12 upward. I know that the acceleration is 9.8 to 9.8 down. I also know that the time, well, let's just write it as t, and I know that it's traveled a displacement delta y, let's call that y. Now for B, the VI is equal to 5.4 downward, acceleration is equal to 9.8 downward. The time is going to be the time for A, but minus 2 seconds, so t minus 2, because it's traveling for a shorter time despite being thrown, but because it was thrown 2 seconds later. And delta y is going to be the same because it's thrown from the same building. Now we need to find a set of equations that we can use and then equate simultaneously or solve simultaneously to then figure out what the time is. So the equation that I'm going to use is delta y is equal to vi delta t plus half a delta t squared. And I'm going to apply that for both. So here it's going to be y is equal to, now I need to choose a direction as positive. I'm going to go ahead and I'm going to choose down as positive. You can choose up as positive if you want. So for A, I'm going to have minus 12 times t plus half into 9.8 and then times t squared. Then for B, let's draw a line. I'm going to have y is equal to, same down as positive. Now it's going to be 5.4 times t minus 2 plus half into 9.8 and then t minus 2 all squared. Now we know that both the balls would drop from the same height, so we can equate the y values. So y equals y. So we're going to have minus 12t plus 4.9 t squared is going to equal, let's simplify a bit, so 5.4 into t minus 2 plus 4.9 into t minus 2 all squared. Now from here, it's just a matter of solving, simplifying and then solving. You can use your calculator as well. So the calculator, if you solve it, your calculator will give you t is equal to 4 seconds. So they both hit the ground at 4 seconds. Okay, 3.1.2, solve for z. So basically solve for the height at which A or B was thrown from. So now it's just a matter of substituting this value back into either one of the equations. I'm going to substitute it into A, and I'll explain why in a minute. So for A, we know that y is equal to minus 12. Now we know the t value. So 4 plus half into 9.8 times 4 squared. And that's going to give us a value of 30.4 meters. Now you just got to remember that if you are going to substitute for B, you just need to be careful, because the time that you're going to substitute for B is not going to be 4. The time you're going to substitute is going to be 2, because B is only in the air for 2 seconds. The value t on the graph is representing the time from the moment A was thrown. So that's why I substituted it in the formula for A. So 3.1.3. They want us to solve for y. So y is basically the maximum height of the movement of A. So at max height, So at max height, I know that Vf is equal to 0. Now, assuming I'm trying to keep the direction constant here, down is going to be positive. So I'm going to say Vf is equal to Vi plus A times delta t. Now, I need to work out what delta t is first, and then I'll be able to solve for the max height. So 0 is equal to, now A was thrown at 12 meters per second upward. I've chosen down as positive. So here I'm going to have minus 12 plus 9,8 times t. So t is equal to 1,22 seconds. So it takes A 1,22 seconds to reach this max height. So all I need to do now is substitute that value, the time of 1,22, back into an equation which can then give me the height. So I'm going to substitute it here. I'm going to say that y, or delta y, is equal to Vi delta t plus half A delta t squared. So I want to know how far did A travel in that 1.22 seconds. So again, I'm keeping down as positive here. So delta y is equal to minus 12 times 1,22 plus half into 9,8 times 1,22 squared. And that's going to give me a delta y value of minus 7,35 meters. But remember, this is minus 7,35 downward. So it means that it's 7,35 meters upward. So A was at a height of 30.4. It was then thrown a height of 7,35 up. So the total height, the height at Y, that's going to equal 30.4 plus 7,35, which is equal to 37,75 meters. Now, taking a look at this last question, question 3.2. On the same set of axes, sketch the velocity time graphs for A and B whilst they are in free fall. Label the graphs A and B for ball A and for ball B respectively. Clearly indicate the following. So initial velocity, the time at which each ball is thrown, and the time at which they strike the ground. Now again, I'm keeping down as positive here. So for ball A starts at minus 12, because remember, I've chosen down as positive and A was thrown upward. For ball B, it was thrown at a VI of 5.4 meters per second downward, so that's a positive value. So on my velocity time graph, I'm going to have the following. I'm going to have my axis here, I'm going to have velocity, and I will have time here. So time is in seconds, velocity is in meters per second. So ball A at the start, I'm going to go from minus 12 here. And we know from the previous calculation here that it takes 1.22 seconds to stop at max height. So at 1.22 seconds, I'm just going to estimate here, 1.22, it stops there. So all I need to do is I need to join this line like so. Just join that. Okay? Now, for ball B, I know that it was thrown 2 seconds after ball A. So at 2 seconds, so let's say that 2 seconds is there, and it was thrown with a velocity of 5.4. So I'm going to assume just roughly that 5.4 is roughly there. So where these two intersect, so somewhere there, I'm going to draw the motion for ball B. And remember, the lines should be parallel because the gradient gives me the acceleration, which we know to be 9.8. Now, they want us to show the time at which both strike the ground. So they both strike the ground at 4 seconds. So I just need to extend this slightly. So that will extend like so, and that will extend like so. And that's basically it. Of course, I haven't drawn it to scale. I haven't used any measurements or anything like that. So your mileage may vary. Question 4. Two trolleys A and B of masses 1.5 kilograms and 2 kilograms respectively are held in a stationary position
on a straight horizontal frictionless track with a compressed spring between them. The trolleys are released and the spring takes t seconds to return to its natural length. The spring then falls to the ground. Trolley A moves to the left and trolley B moves to the right, and it moves up a frictionless inclined plane, rising to a maximum vertical height of 1.5 meters as shown in the diagram. So they didn't tell us to ignore the rotational effects on the wheels. Question 4.1, I'm not going to answer it, but I'm going to explain why it was asked. So the question says, write down the principle of conservation of mechanical energy. We know this, but the reason why they are asking this instead of a momentum question is because in question 4.2, we need to use the mechanical energy rather than conservation of momentum to answer it. So in question 4.2, they ask us to calculate the speed of trolley B at the bottom of the inclined plane. Now, we can't use principle of conservation of momentum. We got to use mechanical energy. So I'm going to say that mechanical energy at the bottom is going to equal the mechanical energy at the top. And the reason why we can use this, aside from the fact that they've given us a clue, is because this is frictionless. So no energy is going to be lost. Now at the bottom, there's no height. So we're going to have EK only. And EK is half the mass, so half of 2, and then V squared. And that's going to equal, at the top, there is no speed. It stops at the top. So there's no kinetic energy. So you're only going to have potential energy, which is mgh. So 2 times 9,8 times 1,5. We can then solve for V, and V is equal to 5,422 meters per second. They ask for speed, so we don't need to indicate a direction. Question 4.3.1. For the t seconds that the spring takes to return to its natural length, calculate the change in momentum of trolley B. Now, the whole thing about the spring is just there to throw us off. The spring really doesn't do anything. It doesn't affect our calculations anyway. So calculate the change in momentum. The change in momentum is delta P, and that's equal to P final minus P initial. I'm going to choose right as positive here. So remember, momentum is mass times velocity. The mass of B is 2. The velocity is 5,422, and then minus 0 because initially it was stationary. So that's going to give me a change in momentum of 10,844 kilograms meters per second to the right. It's positive. Question 4.3.2 says, write down the change in momentum of trolley A. Write down, meaning we don't need to do a calculation. So what would it be? So we know that the change in momentum of the one object must be the change in the momentum of the other object, but in the opposite direction. So if B had a change in momentum of 10,844 to the right, then A must have a change in momentum of 10,844 kilograms meters per second to the left. Question 4.4, calculate the speed of the trolley after t seconds. We know its change in momentum. We know its initial momentum, so we can calculate its speed. So we can simply say, again, I'm choosing right as positive here. And if right is positive, then this change in momentum value must be negative. So minus 10,844 is equal to, well, 1,5 is the mass. The velocity v is what we want. And then minus 0, because like b, it was stationary initially. So we can solve for v. V is going to equal minus 7,23 meters per second. But remember, this is to the right. So we can't leave our answer like this. We change the direction and change the sign. So V is then equal to 7,23 meters per second to the left. Question 5 says a constant force of F is applied at an angle of 30 degrees to the horizontal on a crate of mass 6 kilograms that is initially at rest as shown in the diagram below. A constant frictional force of 10 newtons acts on the crate as it moves from rest at point A along a horizontal surface to point B. The distance between A and B is 1.5 meters. The speed of the crate at point B is 2 meters per second. Question 5.2 says, draw a label free body diagram showing all the forces acting on the crate as it moves.
Now, as it moves, it's going to experience, well, a force of gravity, a force applied, a normal force, and friction. Question 5.3 says, using energy principles only, calculate the magnitude of force F. So I'm going to use the formula WNC is equal to delta EK plus delta EP. Now, the work done by non-conservative forces here, the non-conservative forces are the force applied and the friction. So the work done by the force applied is going to be the force applied times delta x, which is 1.5, and then cos theta. So what is the angle between the force and the displacement? Well, it's given to us as 30 degrees. So cos of 30 degrees plus friction. They tell us the friction force is 10 multiplied by delta x, 1.5, and then cos of theta, or cos of the angle. So friction is 180 degrees away from the displacement. So it's going to be cos 180. And that's going to equal delta EK. So since it's starting off with a velocity of 0, it's at rest, the EK initial is going to be 0. And also, there's no change in the height, so there's no change in EP. So the change in EP is 0, and the EK initial is 0. So there's only EK final. So EK final here is half. The mass is 6, and then v squared. Well, we know the velocity at b is 2 squared. So now the only thing we don't know is Fa. We can solve for Fa. F, or Fa, whatever you want to call it, is equal to 20,78 newtons. Question 5.4. A 2 kilogram object is placed inside the crate. What effect will this have on the work done by the same force F when the crate is again moved from point A to point B? So it's going to remain the same. So remains the same. And that's because the work done by this force is equal to the force times delta x times cos theta. The force is not changing, the delta x is not changing, the angle is not changing, and so the work done by the force should not change either. Question 6 says, a stationary listener standing on the roadside records the wavelength of the sound emitted by the siren of a police car traveling at constant velocity. So I'm going to make a note here, a stationary listener. So that means that VL is equal to 0. Record the wavelength of sound. Okay. In the wavelength time graph below, not drawn to scale, lambda L is the wavelength of the sound recorded by the listener, and lambda S is the wavelength of the sound emitted by the siren. So from the graph, I'm just going to make a note. Lambda L is equal to 0.40 meters, and lambda S is equal to 0.38 meters. Take the speed of sound in air to be 343 meters per second. Question 6.2. Is the car moving towards or away from the listener? Give a reason for the answer. Now, I'm going to use an equation to explain this. The equation is V is equal to F times lambda. V is the speed of sound in air, and it is a constant value. Because it is a constant value, it means that F and lambda are inversely proportional. So because lambda L is greater, we have a greater lambda L compared to lambda S, that means the frequency will be low. So we're going to have a low frequency. And since the frequency is lower, it means that the car is moving away. Question 6.3.1. Calculate the frequency of the sound emitted by the siren. So V is equal to F times lambda. So 343 is equal to F, so that's the frequency,
multiplied by the lambda. Now we need to be careful. We have lambda L and lambda S. We are interested in the siren itself, so the sound emitted by the siren, so the source. So we're going to substitute in 0,38. That means that the frequency is going to equal 902,63 hertz. Question 6.3.2, calculate the magnitude of the velocity of the car. Here it's worth 6 marks, so there's probably going to be more than one equation that's going to be used. The first thing I need to do is work out the frequency that the listener hears. So the frequency of the listener is going to be equal to, I'm just going to rearrange this equation from 6.3.1. It's going to equal 343 divided by 0,40, and that's going to equal 857,5 hertz. Now I can use the Doppler formula. So since it is moving away, the formula is going to be FL is going to equal V minus VL divided by V plus Vs multiplied by Fs. Now we just have to substitute. 857.5 is equal to 343. The listener is stationary, so VL is 0, divided by 343 plus Vs multiplied by the source, which is 902,63 as we calculated in 6.3.1. Now we can rearrange, or we could use our calculator. Vs is therefore equal to 18,052 meters per second. Question 7 says P is a positive 2 nanocoulomb point charge. X is a 0.6 centimeters away from point P as shown in the diagram below. Question 7.1, calculate the magnitude of the electric field at X. So 7.1, we will say that the electric field is equal to KQ divided by R squared. K is 9 times 10 to the power 9. Q is the charge, so 2 times 10 to the negative 9 divided by R needs to be in meters, so that's 0.06 squared, and that gives us 5,000 Newton coulombs. And they ask for magnitude, so we don't need to give a direction. Question 7.2. Point charge S with a charge of minus 2 nanocoulombs is placed 4 centimeters to the right of charge P, as shown in the diagram below. Draw the resultant electric field pattern due to P and S. Now P is positive and S is negative, so there will be an interaction. So I'm going to represent it like this, positive and negative, and there will be an interaction like this. Now remember, the field lines should not touch, so just be careful with that. And remember, the arrows go away from the positive and toward the negative. Now you can draw as many or as few as you like. However, just make sure that the number of lines on the positive and the negative are the same because they have the same magnitude of charge. Now, question 7.3 says a third point charge T is placed 2 centimeters to the right of S as shown in the diagram below. Point charge T experiences a net electrostatic force of 2.5 times 10 to the negative 4 newtons to the left. 7.3.2 says, what is the polarity of charge T? So is it positive or is it negative? Now the way that I answered this is you have to do a test here. So if T is positive, then that means that P is going to want to repel it and it's going to want to push it, and it will push it with some force, but not a lot of force because it's quite far apart. Now if T is positive, then it's also simultaneously going to be attracted to S because S is negative. Now that force of attraction is going to want to pull it left, and it's going to pull it left with a greater force than it's being repelled because S is closer to T. And does that work? Yes, it does work, because we can see that the resultant then is going to be to the left. So let me just sketch that out again for you. So if t is positive, like we are assuming it is, so if t is positive, it's going to be attracted to S. So let's say force of S. But it's also going to be repelled by P. So it's going to want to be pushed to the right. But the force at which it's being repelled is not going to be as much as the force as if it's being attracted, because P is further away. Remember, as you get further away, the force weakens. And so, yes, this makes sense, because then we're going to have a net to the left, which is what the question is telling us we do have. So the answer here is that it is positive. Question 7.3.3 says, calculate the magnitude of charge T. Now, I've already drawn a kind of free body diagram, if you will, and we can simply use that to help us solve the question. So I'm going to choose left as positive. That means F net is going to equal Fs, so the force that S is pulling it with, minus Fp. So F net, they tell us, is 2,5 times 10 to the negative 4, and it's positive value because I've chosen left as positive. Now Fs is going to be kq1 q2 over r squared, so 9 times 10 to the 9. Q1, let's call it T, we don't know what T is. Q2 is going to be the charge of S, which is 2 times 10 to the negative 9. Remember, when you are using these force formulas, Coulomb's law formulas, we do not include the sign. So then divided by the distance between S and T is 2 centimeters, so 0,02 squared. Then we're minusing 9 times 10 to the 9 into the charge of T into 2 times 10 to the negative 9 divided by P is 6 centimeters away from T, so that's 0.06 all squared. We can then solve for T, and T gives us, or the calculator rather, gives us 6.25 times 10 to the negative 9 coulombs. Question 8 says, L1 and L2 are two light bulbs that have the following ratings. So they give us the ratings, they give us the voltage and the power. The two light bulbs are connected in the diagram below. The battery has an internal resistance of 0.6 and the conducting wires have negligible resistance. There's also a resistor R1 and R2. R2 is 4 ohms and R1 we don't know. Question 8.2.1 says calculate the reading on ammeter A2. So A2 is this one. It is reading the current that's going through L2, L2 being that light bulb. So we know the voltage and we know the power. If we want the current, we can say power is equal to V times I. Power is 48, and that's equal to V is 32 multiplied by I. I is then equal to 1.5 amperes. So this needs 1.5 amperes to go through. Question 8.2.2, calculate the reading on ammeter A1. So A1 is this one right here. So what we can do is we can use L1, figure out the current going through L1, add them up, and then we can work out A1. So looking at L1, I know the power, I know the voltage, I can work out the current. So just like I did before, power is equal to 36, that's equal to 20 times I. That means I is equal to 1.8 amperes. So the current reading on A1 is going to be 1.8 plus 1.5, which is equal to 3.3 amperes. So this is 3.3 and this is 1.8. Question 8.2.3 says calculate the resistance of R1. Okay, so if we look at L2 for a second, we can see that it's using up 32 volts. So this whole thing, this whole branch is using up 32 volts. Now we know that the voltage in parallel needs to be the same. So if L1 is using up 20 volts, that means R1 must be using up 12 volts, because 12 and 20 gives us 32. So the voltage for R1 again is going to be 32 minus 20, which is 12 volts. And we know the current going through R1 because we just worked it out in question 8.2.2. So we can say V is equal to I times R. The voltage for R1 is 12. The current going through R1 is 1.8 multiplied by R. R is equal to 12 divided by 1.8, which is 6,67 ohms. Let's take a look at question 8.2.4. Calculate the EMF of the battery. So, of course, we can use the EMF formula, but I'm not going to work out the entire resistance here because I'll be honest, I'm a bit lazy. So what I'm going to do is I'm going to work out the V external. So V external here is going to be the voltage in parallel plus the voltage in series. The voltage in parallel is 32. The voltage in series, I actually don't know. I need to work it out. So what I'll do first is I will look at this resistor. I know its resistance. I also know the current going through it, which is 3.3. I can work out the voltage. So V is equal to IR, 3.3 multiplied by 4, and that's equal to 13.2 volts. So plus the 13.2 volts there, that's going to give me a V external of 45,2 volts. Now EMF is equal to V external plus V internal. So V external we worked out as 45,2. V internal is equal to I times small r. So 45,2 plus total current 3,3, and the internal resistance is 0,6. And if you add them up together, we're going to get 47,18 volts. So that's the EMF. Now, taking a look at question 8.3, 8.3 says bulb L1 burns out. Assume the resistance of L2 remains constant. So L1 burns out, so this means that this whole branch is gone. That whole branch is gone. That current will obviously change, but that whole branch is gone. So this is my new circuit. Okay. So that's my new circuit. Question wants to know, will bulb L2 continue to glow after L1 burns out? Choose from yes or no. Support your answer with a suitable calculation. So what I'm going to do first is I want to work out what the resistance of L2 actually is. And the reason why I want to do that is because I want to then look at what the new current is going to be. If the new current exceeds 1.5, remember the 1.5 is the rated current. That's the current that L2 needs to work because we use the rated power and we use the rated voltage. So then we can compare. If the current is going to be greater than the 1.5, then it's not going to work. So to do this whole calculation, I need to then work out what the resistance is. So I'm going to use the formula again for L2. I'm going to say power is equal to V squared over R. The power is for L2, it's 48. That's equal to V squared, so 32 squared divided by R. R is then equal to 21,33 ohms. Now, I want to work out what the new current is going to be. So I'll use the EMF formula here. So EMF, well, I know the EMF, I just worked it out, 47,18. So 47,18 is equal to the current into the total resistance is going to be 21.33 plus the 4 ohm that's still in the circuit, so 4, plus the internal resistance 0,6. And if I work out the new current, I get a new current value of 1,82 amperes. So 1,82 is greater than the rated 1.5. So therefore, it will not work.
Question 9 says, the graph below shows how the induced current in a generator varies with time. Question 9.1, name the type of generator. Is it AC or is it DC? So because the graph is not going below the x-axis, it means that this is going to be a DC generator. Question 9.2, state the energy conversion that takes place in this generator. For a generator, you will have mechanical energy being converted to electrical energy. Question 9.3, give a reason why this generator is not suitable for transmission of electricity over long distances. This is a theory question. There's actually a few answers, but one of them is there is high energy loss. So that is one of the reasons why it is not suitable. Question 9.4, calculate the frequency at which the coil rotates in the generator. Now, just like in transverse waves, we can calculate frequency by saying the number of waves divided by time. So I have here, that's half a wave, so 0.5, and half a wave took 0.01 second. So that's equal to 50 hertz. Question 9.5, okay, that's the definition. Question 9.6, calculate the root mean square current delivered by the generator. Now from the graph, we can see that there is a max current, so I max is equal to 1,2 amperes. So IRMS is equal to I max divided by square root 2. So 1,2 divided by square root 2, which is equal to 0.85 amperes. Question 9.7. The graph below shows how the induced current varies with time after a change was made. So they changed one singular thing. And the question says, fully describe the change that was made. Now, we know that the frequency is 50 hertz. That means that is the number of turns in a second. So it's spinning 50 times per second. Now, if we look at it, you have half a wave. You have half a wave in 0.02 seconds. So frequency is now half, so half a wave in 0.02 seconds, and that's equal to 25 hertz. So they essentially decreased the frequency. They slowed the rotation. And that decreased, or you could say decreased the frequency. The last question in the paper, question number 10. 10.2. Red light, blue light, and green light are shone simultaneously on a sheet of potassium as shown in the diagram. Each color of light consists of a single frequency. Two maximum frequencies of the ejected electrons are possible, namely those two. Each ejected electron has only one of these maximum kinetic energies. So remember, red, blue, and green light. Question 10.2.1, which color of light is responsible for ejecting electrons that have a maximum kinetic energy equal to 2.65 times 10 to the negative 20? So the colors again, I'm going to go through the colors in the spectrum. So we have R, O, Y, G, B, I, V. Now red has a high wavelength, but it has a low frequency. So the colors were red, okay, so that's red done. Then we had green, and then we had blue. So blue has the highest frequency of those three. Now remember that energy, or EK, is proportional to the frequency. So a higher frequency means a higher EK. So blue is actually going to have the highest kinetic energy. So it's going to emit a photon or a photoelectron with a kinetic energy of 6.96 times 10 to the negative 20. That means the other one must be for green, 2.65 times 10 to the negative 20 joules. So the answer to the question, which color is responsible for ejecting electrons that have a maximum kinetic energy of that, it's going to be green. And explain the answer, well, we've already explained it. Green has the second highest frequency of the lot, so it's going to have the second highest kinetic energy. Question 10.2.3 says, the electrons with a maximum kinetic energy of that are ejected by a light that has a frequency of that. Calculate the frequency of the light that ejected electrons with a maximum kinetic energy of that. So essentially they are asking us calculate the frequency of the blue light. So what we can do, and it was 5 marks, so that means we're going to need to do 2 separate calculations. So I'm going to start with the formula. E is equal to W naught plus EK max. Now remember, E is equal to HF. So H is 6,63 times 10 to the negative 34. And the frequency of the green light they've given us is 5,85 times 10 to the power 14. That's equal to W naught. That's the work function of the potassium metal. We don't know what that is, so we leave it as W naught. And then plus the kinetic energy. So 2,65 times 10 to the power minus 20. We can then solve for W naught. W naught is equal to 3,61 times 10 to the negative 19 joules. Now, because the green light is being shone, because the green light, the red light, and the blue light are all being shone on the same metal sheet, the same work function will apply. So we can then do the calculation again, but this time changing some of the values. So E is equal to W naught plus EK max. Now when we're using the kinetic energy for the blue light, the EK value here is going to be 6,96 times 10 to the negative 20, and plus, we know the W naught value, 3,61 times 10 to the negative 19, and that's equal to, H is the same, so 6,63 times 10 to the negative 34, and then multiplied by the frequency. This is now the frequency of the light that we are interested in. So frequency is therefore equal to 6,5 times 10 to the power 14 hertz. And that is expected. We expected a frequency that's higher because blue has a higher frequency than green. Question 10.2.4, the intensity of the red light is increased while the intensities of the blue light and green light remain the same. What effect will this change have on the rate at which electrons are ejected? Choose from increase, decrease, or remain the same. It's not going to have any effect because the red light was not ejecting any photoelectrons or electrons anyway. So it's going to remain the same. Okay. Now moving on to question 10.3. Some of the atoms of a hot gas made up of a single element are in an excited state. The spectrum formed by the hot gas is observed on a screen in a dark room. The spectrum consists of specific colored lines on a black background. Name the type of spectrum formed. So this is called an emission spectrum. So you should just remember that a hot gas, if it's hot, you will have an emission spectrum. And if it's cold, you will have an absorption spectrum. So hot gas emission spectrum. Question 10.3.2, explain the presence of the colored lines in the spectrum. So essentially what's going on here is the colored lines. So let's say we have a photoelectron that is here. It has energy, right? It is a hot gas, which means it has extra energy. So it's in this higher energy level. It is in this excited state. When it goes down, right, it's going to release energy, right? And that energy is emitted onto the black background in the form of light. So when it decreases, So let me just write it here. The colored lines correspond to the frequency of the emitted photons or photoelectrons when an electron is moving or moves from a high energy state to a low state. So it's currently in that excited state and it's going to go back to the ground state. When it goes down, it gives off energy, it gives off light of a specific frequency that then shines onto that metal, not onto the metal, onto the black background in a specific color. And that's the whole paper. Guys, if you stuck around, thanks so much for watching. Don't forget to leave a like, share, and subscribe for more. I'll see you in the next one. Bye bye.